All right, hey everybody, day 6. This is day number 6. Demoivre's theorem and multiple roots. Let's get started. All right, so here is Demoivre's theorem. What Demoivre's theorem says is that if I take some number, some complex number written in polar form, all right, and I take it to some power, to the n power. All that means is that you take r to the nth power and theta times n. Okay, so r cis theta to the nth power is r to the nth cis theta times n. Alright, because look at this mess right here. This example would be an absolute mess. You'd have to expand and then simplify. It would be just terrible. Well, root 3 plus I is actually equal to, what would that be? 2 cis pi over 6. If I take that thing to the 4th power, I would get 2 to the 4th cis pi over 6 times 4. Right, that's using this theorem right here. That's Demoivre's theorem, which is 16 cis 2 pi over 3. Okay, same thing over here. If I were to do this for root 3 minus I, that would be 2 cis, that's in quadrant 4, quadrant 4, so that'd be 2 cis negative pi over 6. If I take that thing to the 2nd power, that'd be 4 cis negative pi over 3. Okay, now what am I doing with these two things? I'm taking their product. Okay, now here's another part of Demoivre's theorem. When I take r cis theta and I multiply it by q cis beta, multiplication, kind of like logarithms and exponentials, would just be product on the outside, cis, you're going to add those angles. Okay, if you are dividing, just for a reference, if it was r cis theta over q cis beta, we would take and divide our coefficients, but we would subtract our angles. So in this case, we're doing a product. Therefore, if I'm multiplying these two polar complex numbers, it'd be 4 times 16, which is 64, cis, and then I would add together their angles. 2 pi over 3 plus negative pi over 3 is just going to be pi over 3. And that would be it. If I wanted to put that back into Cartesian form, I would probably sketch it. So it would be in quadrant 1, we'd have a hypotenuse or a modulus of 64, an angle of pi over 3, so that means this would be 32, and this would be 32 I root 3. So the answer to that, if we would have expanded it and combined like terms, would be that. Alright, so that's Demoivre's theorem. Let's use it a little bit further. Okay, what are the 3 roots of negative 1? Well, negative 1 is technically a complex number. It just has 0i as its imaginary portion. So if I wanted the 3 roots, let's say I wanted the 3 roots of negative 1. The first thing I would want to do is I would want to put this in cis form, because then I can use Demoivre's theorem. Well, negative 1 is the same as 1 cis pi, right? If I were to put this on a diagram, negative 1 would be right here. So therefore, in order for me to get there, I'd rotate out, extend out 1, rotate pi units. Okay, so it's 1 cis pi. So how do I find the roots? Well, I would take the third root of both sides. Okay, which would give me z equals, the third root of 1 is still 1. And then I take pi and multiply it by 1/3. However, let me backtrack here for a moment. This is going to happen an infinite number of times. So it's going to happen every 2 pi units after or before pi. Alright, so really what I'm doing is I'm accounting for all possible solutions by doing this. So I distribute that 1/3 to pi, which gives me pi over 3, and then the same thing to the 2 pi k. So that's going to account for every possible root that could happen. Now what I want to do is I want to set k equal to 0, k equal to 1, and k equal to 2. You always want to start at k equals 0, and then once you get to k equals 2, which is one number less than this, we would stop, because if we went to k equals 3, it would loop back around and we'd get the same solutions over again. So I'm going to find the 3 roots of -1. Alright, so if I plug in a 0 for k, I get cis pi over 3. That was for k equals 0. For k equals 1, I get cis. I add pi over 3 plus 2 pi over 3, which is 3 pi over 3, which is pi. And then I add 2 pi over 3 yet again, and I get 5 pi over 3. However, this is not complete, because we always want our argument to be between -pi and pi. Therefore, this last one here, I would write as -pi over 3. Awesome. So I believe that this would be okay. This would be a decent answer, and actually entirely correct, as long as you're asked to keep it in polar form. If you're not, then you have to convert it to Cartesian form, which is not that bad. Okay, and as you'll see later in Argand diagrams, we want it in this Cartesian form. So cis pi over 3, these are just unit circle. How do I know that? Because the modulus is 1. So I would have here, what would that be? 1/2 plus I root 3 over 2. Then I would have z1 equals -1, right? And then I'd have z2 equals, that would be 1/2 minus I root 3 over 2. Okay, so those would be the Cartesian roots of -1. Okay, cool. So that's just an overview on how to find the roots in both polar and Cartesian. All right, let's keep moving. I think I'd like to do one of these two. How about if I do, let's see here. Let's do number 5e. Okay, so this right here, 64i, written in polar form, or in complex form, would be 0 plus 64i, right, which would be right here on the imaginary axis. All right, therefore, written in polar form, it would be 64 cis pi over 2 plus, now check it out, I'm going to write this as 4 pi k over 2. Okay, I know that the modulus is 64. I know the angle of rotation, that argument is pi over 2. I made this 2 pi k into a 4 pi k over 2 to keep a common denominator. And now I go, so I'm going to take the cube root of both sides. Okay, so the cube root, and we got to do a little bit of work here. it looks like to me, if I did the cube root of 64, I'd get 4. 4 times 4 times 4 is 64, yep. And then cis, that would be pi over 6 plus 4 pi over 6. Don't forget the k. Okay, so now I only need 3 values here. I'm going to go k equals 0, k equals 1, k equals 2, because I'm looking for the 3 roots of 64i. So I'm going to plug in k equals 0, k equals 1, and k equals 2. I plug in a 0, I get 4 cis pi over 6. I plug in, or a 0, I get that. I plug in a 1, I get 4 cis 5 pi over 6. And then I plug in a 2, I get 4 cis. I'm going to get, what would that be, 9 pi over 6, which is this, so 9 pi over 6, which is the same as 3 pi over 2, which is the same as negative pi over 2. Alright, so let's write these polar form into Cartesian. That would be 4 cis pi over 6. So that would be 2 root 3 plus 2i. Z sub 1 would be negative 2 root 3 plus 2i. And z sub 2 will equal, oh, that's a nice one. What would that be? 0 minus 4i. Yep. Cool. So there are our Cartesian coordinates for the 3 roots of 64i. Alright guys, that's it for today. Good luck with the homework. Any questions are always welcome. Have a great one.